Metasurfaces, the future of quantum information processors, but here's where it gets controversial. Metasurfaces could potentially revolutionize quantum computing by enabling ultra-thin, robust, and scalable photonics processors instead of relying on traditional optical components. A groundbreaking study from Harvard University, Optical, led by Federico Capasso and his team, showed that metasurfaces designed with nanoscale light manipulating patterns can create complex entangled photon states to perform quantum operations, like those seen in larger devices, without requiring extensive fabrication. This approach eliminates the need for waveguides, beam splitters, or bulky optical chips, making quantum systems more compact and stable. Graph theory plays a crucial role in designing these metasurfaces, as it helps visualize and predict how photons interact in complex networks. Researchers at the Harvard Center for Nanoscale Systems collaborated with Marco Lonchar's team to develop this technology. We're introducing a major technological advantage when it comes to solving the scalability problem, said Carolus M. A. Youssef, the first author. Now we can miniaturize an entire optical setup into a single metasurface that's very stable and robust. The work highlights a shift toward error-resistant metasurfaces that offer advantages such as reduced fabrication complexity, cost-effectiveness, and optical loss minimization. While conventional methods like waveguides and microchips face challenges in scale, metasurfaces could redefine quantum computing by offering unprecedented control over light at room temperature. By leveraging graph theory, scientists can efficiently design and operate these systems, bridging the gap between quantum optics and practical applications. Harvard researchers revolutionize quantum photon control with metasurfaces. Quantum leap. Harvard researchers tame light with ultra-thin metasurfaces, revolutionizing quantum computing. Imagine a world where quantum computers are as small as a chip, yet pack a punch that rivals their bulky counterparts. This is the promise of a groundbreaking discovery by Harvard researchers, who have successfully harnessed the power of metasurfaces to control quantum photons with unprecedented precision. The scalability conundrum. As quantum computing advances, a significant hurdle remains: scalability. Conventional optical devices necessary for quantum operations become increasingly cumbersome as the number of photons grows. But here's where it gets innovative. The Harvard team, led by Federico Capasso, has demonstrated that metasurfaces, flat nanoscale devices with light manipulating patterns, can create complex entangled states of photons, performing quantum operations akin to those of larger optical devices. Graph theory, the secret sauce. So how did they achieve this feat? By leveraging graph theory, a mathematical branch that represents connections and relationships using points and lines. This novel approach allowed the researchers to visually map entangled photon states, predicting their behavior in experiments. But here's the controversial part. Could this application of graph theory to metasurface design disrupt traditional quantum computing methodologies? A new era for quantum optics. The implications are profound. Metasurfaces could consolidate multiple optical components into a single ultra-thin array, simplifying quantum optical setups and paving the way for room temperature quantum technologies. This breakthrough, detailed in Science, was made possible through funding from the Air Force Office of Scientific Research, Award No. FA 955021312, and the National Science Foundation, Award No. ECCS 2014-1558. Expert Insights. Neil Sinclair highlights the fresh perspective this work brings to metasurface understanding, design, and application, particularly in generating and controlling quantum light. Carolus M. A. Youssef emphasizes the technological advantage of miniaturizing entire optical setups into a single, stable metasurface. The future of quantum computing. As researchers continue to push the boundaries of quantum technology, questions arise. Can this metasurface approach truly overcome the scalability challenges in quantum systems? How might this innovation impact the development of quantum sensing and lab-on-a-chip capabilities? Share your thoughts. Do you think this breakthrough will revolutionize quantum computing, or are there still significant hurdles to overcome? Join the discussion in the comments below. Key takeaways. Harvard researchers demonstrate metasurface control over quantum photons, achieving scalability comparable to larger optical devices. Graph theory is used to design metasurfaces, offering a novel approach to quantum optics. Potential applications include room temperature quantum computers, networks, quantum sensing, and lab-on-a-chip technologies.